Hello? Hi Linus, how are you? Do you have a new Zoom link?
Hi, fine, thank you.
Okay, the Zoom link is new. Do you see it?
I am going to look right now.
Yeah, please check email because they have changed it.
I saw a note from yesterday, 22 hours ago.
Just 10 minutes ago. They have changed the link just in the last second. I sent you in email, new Zoom link.
I am scanning my email. Is it this one? 10 hours ago, you asked for my slides.
Yeah, just let's sort out the links first.
I am not seeing anything from you.
It says, hi all, use new Zoom link. I am resending it again.
No, send it again.
Trying again. Hi Victor, we are just trying to get Linus online with new Zoom link. Linus, I have sent you the link to this phone in the text message, and also I emailed link in the Gmail.
Gmail
Yes.
says that it is not connected.
Okay. Can you get this link on your phone? I sent the link to your phone in the text message.
All right, I'm looking at my phone to figure out how to. I might hopefully I won't hang up on you while I do this. Let me see if I can find it.
Okay, but it's sent. But Victor, have you got the link via email?
Ryan, do you want to share your
It should be sent now.
download?
Yes, but I can also send it, resend it.
Starting soon.
If you have an email address for me on Slack, I can
screen.
email there, no problem.
I connect this link on the phone, so I'm going to do that again.
Okay, I'm waiting for you. Okay, I'm hanging up, so please connect. Hi, Peter.
Hi. Yeah, apologies for the hassle with the Zoom links, but it's it should be.
Yeah, we are in trouble with this because the first speaker is kind of limited in his capacity to deal with such situations. So you might need to handle this. He was able to get the first link, but now he's not able to find it in.
Yeah, if it's any help, I can email, but I'm not sure if that's the way.
I think we'll have to wait a little bit and have multiple phone calls along the way because of this. Okay, let me start making more phone calls to make sure people check their emails. Hi, Nikolai, are you joining the new link? Yes.
Yes.
There is a new link. There is a new link. Hi, thank you, Nikolai. Okay, we are having progress. We have the first speaker.
We're gonna get all the behind the scenes stuff here.
Oh, exciting.
And this is the webcam. So it looks like
We have the first Linas Vepstas. And one more speaker.
Let's see. This is
Okay, we have Nikolai Mikhailovsky. Hi, Nikolai.
Hello, everyone.
Hi, Linas. Do you hear us?
Can you hear me?
Great.
Absolutely.
Example? Yes.
Okay, so I think we are missing just one more speaker. And actually, we can start. Peter, I think, Linus, let us know when you can start.
I can start it.
Okay, Peter?
I can start immediately. I'm planning to do a share of the window.
Oh, okay, just 1 second. So let me ask when we can start.
It'll be kind of a self-managed.
Sure, yeah.
I mean, unless someone's coming to.
Yes, I think we can start. I'm just going to request everybody to please mute themselves when not speaking, because
Yes,
it becomes a bit
sure.
messy.
I think everyone is muted, unless the.
There's quite a lot of people not muted. So please don't be offended if I mute you.
1 second. Let me see who is muted. Okay. Well, Linus is the first speaker. He is not muted. Zahar, can you mute yourself? So Zahar. Peter, I think we have sound coming from INLP.
Okay, I can mute that.
Okay.
Just let me know when I
Now
should
we are
mute.
good. Now we are good. So we have just the first speaker. So we have Mukul, we have Zahar, we have Linus, we have Peter, we have Nikolai, we have Victor. Well, we can start. Let us know.
I see that Ben managed to schedule something else at exactly the same time to draw away our audience, as it were.
I don't know. So
Yeah,
Peter,
It goes on your
That's,
chart right here, room 1.
Peter,
that's it. Yes, we can start. I will stop sharing my starting soon screen, and I'll focus on Linus's share.
okay. So let's go ahead. So hello everyone. So we are starting the second workshop on the interpretable natural language processing. In the first talk, we'll have Linus Vepstas telling us some background, theoretical and fundamental backgrounds of this direction, and provide some up-to-date results. After that, Nikolai Mikhailovsky will provide some kind of mathematical justification and his considerations on this regard. After that, I will provide some very latest practical experiments and studies bottom up from the level of individual characters, how the language can be learned and modeled at the character level from the segmentation and tokenization perspective. Then we'll move further to practical applications, and Victor Nosko and Zahar Panimash will tell us how modern neural network can be tailored for conversational intelligence development. And finally, we will have very practical work presented by Mukul Vishwas, who will present how different aspects of human emotions, including sentiment and cognitive distortions, can be extracted from the social media data for financial applications. So Linus, you are welcome to present this virtual environment, and the universe is yours.
Okay, do you see my slides?
Do go ahead.
Are you able to see the title slide here that I'm showing?
Yes, go ahead.
Yeah, it looks like you can. Okay, I'm going to do this talk in 2 parts. The first part is actually going to be the lightning talk from Monday, simply because none of the rest of anything makes sense unless I do the lightning talk first. So some of this you will have heard before, but entertain me. I'll try to be fast about it. Okay, the topology and structure of 3D objects is a challenge for deep learning and neural nets. I found these pictures on Twitter recently. Somebody had asked DALL-E for a coffee cup with a hole and got this image. Another unspecified AI measured a 5.2 meter long cow. right? I can only conclude that AI can see, it just doesn't understand what it sees. And so this talk proposes basically on the next step on a way to obtaining an understanding, and that is a combination of tokenization and grammar. Okay, we already have a tool set for discussing topology and geometry. It's provided by conventional mathematical engineering thinking. These images show triangular meshes, vertex edge lists, AKA graphs. This domain already offers a broad and deep menu of concepts that can be applied. The twist that I'm proposing here is to replace the conventional edge list description of a graph by jigsaw puzzle piece description. Right? Jigsaw puzzle pieces can mate only when the connectors can mate. The mating types are type theory types. There's actually a lot of algebra behind this, a lot of mathematics. I'm going to skip over it. But the upshot is it's a somewhat unconventional graph theory, a somewhat unconventional algebra. It is well known in linguistics. Okay, but first, another example. Here, I've manually segmented an image into some obvious relationships. Certain colors must occur above or below other colors. Certain shapes are shared by all of the colored regions. There is a background setting for the object of interest. The background can be anything. The partially assembled jigsaw indicates what the object is. The sub-assemblies indicate part-whole relationships. I want to dwell on part-whole because there are papers in the deep learning world written by leading figures, right, exponents of deep learning, that lament the lack of part-whole relationships in deep learning and in neural nets. I think Jeff Hinton wrote one of the primary papers on this. And, they can't do something that somehow seems obvious to us. Okay, this is all old news in linguistics. The assembly from parts is not new. It appears explicitly in a figure in paper in linguistics from 1991, the original link grammar paper, and implicitly in even earlier work, once you know what to look for. One of the rediscoverers, E.A. Nida, spoke of assembling words into sentences the same way that chemists assemble atoms into molecules. Again, the bottom slide shows how to bridge from this approach to a statistical approach. It shows a maximum spanning tree parse with the weights indicated in the links. This figure is directly from a PhD thesis from 1998. So again, old news here. In this slide, I'm trying to show that jigsaw pieces provide semantics for symbolic AI. This slide applies the jigsaw connector paradigm to find things that can be seen. On the right-hand side, the type is rather small, but you can see jigsaw pieces for a telescope, a lens, and for eyes. They have the same shape because telescope lenses. Sorry, that was an interruption. Because all these shapes have the same relationship to the perceived object. Linguists have long observed that pure syntax already encodes the shallower layers of semantics. You can get the meaning of words simply by seeing how they're connected to their surroundings. Again, Anton will recognize this image from long before. This is the idea works. Basically, the idea works not just for language, but for vision and also for general sensory domains. On the left-hand side is a clip of a whale song recorded by the National Atmospheric and Oceanic Administration. It has a syntactic structure that can be represented by jigsaw connectors. Note that here there are at least 5 dimensions. There's frequency, intensity, time, the envelope, chirp modulation. More generally, wavelet style decomposition is handy if you're trying to do high-dimensional fractal spaces. I've oversimplified the segmentation to make it fit into this chart, and true structure is going to be more complex. This slide attempts to illustrate some of the random audio filter sequences used to detect features. The task is to discover and data mine good filter sequences, as opposed to having an engineer design one of these things. Standard ML techniques can be applied to achieve this, right? The point here is the jigsaw paradigm. I mean, it's not just pie in the sky. There are actual practical algorithms that can extract this structure. They're old school, they're conventional machine learning. Can deep learning be applied to this? Yeah, possibly. I've got some wild ideas on how to do this. No one has really explored this topic. This is a graph I'll be going into in more detail in the second half of the talk. The point here is I've personally walked partway down this path. I've created the software to do all of this. It's slow going. It's experimental research. There's some theoretical development behind it. This is actually one of the more remarkable results. And I'm sorry if you're expecting to see a lambda-like large language model. This ain't it. This is a Gaussian, this is a bell curve. This shows the distribution of the mutual information between pairs of jigsaw pieces. Recall these jigsaw pieces encode grammatical relationships, right? This is an encoding of the syntax of the language, right? This is remarkable because Gaussians indicate that the underlying data is uniformly distributed on the surface of a high-dimensional sphere. Okay, in physics, this is called a spin glass. The study of spin glasses is brand new. It's a very young branch of mathematics. It's a young branch of physics. It studies probability in high dimensions. It's nothing at all like the low dimensional probability theory of college textbooks. I mean, this is really a whole, if you know probability, this is a whole brand new world that you simply have never seen before. And it really does show up in the publications. And what I find remarkable here is this is an experimental demonstration that the syntax of the English language is maximally efficient in its use of grammatical relationships. Right? These things are uniformly distributed over the entire high-dimensional sphere. It's not bunched up in one spot or another. It's a very nice distribution. Okay, last bit of the lightning talk before I move on to part two. This is the science fiction and conjecture part of the talk. The roadway that I've sketched appears to be recursive. The tricks can be applied repeatedly to mine deeper into the semantic direction. I claim that basically common sense can be learned. It's just a set of frequently observed relationships. This is a panpsychic view of semantics. If everything is a graph, if semantics arises purely from relationships, then all we have to do is mine the relationships ever more deeply. The jigsaw paradigm provides a practical tool, both theoretically and software-wise, with which this can be performed. Don't know how often I get to repeat that. Okay, that's the lightning talk. That took a nice 9 minutes. I'm going to stop the share and I'm going to move on to the next batch of slides, if I can figure out how to do this. I'm going to take a deep breath. Allow, yes. And I'm going to click on the one that says share this PDF. There we go. It looks like you can see the next one, correct?
Yes, all good to go.
Okay, so slide one. Okay, this is sort of now becomes the boring part of the talk where I'm going to actually try to give some of the background for all of this stuff that I just finished going through. I'm going to start with real fundamental basics. So, bear with me if this seems kind of boring, but it's you got to get through with it. Okay, so word pair is just an ordered pair of two words. The number of times a pair has been observed is n. I can assign a frequentist probability. Note the total probability sums to 1. All right, this can be normalized. The star denotes a wildcard sum over all the entries in that location. This can be used to define a mutual information between a pair of words. Sometimes I like to call it lexical attraction because it's not left-right symmetric. There's some confusion because conventional textbooks only present a symmetric version of mutual information. That is inappropriate for ordered pairs. This trips up a lot of people. I keep having to re-explain this. In general, I'm going to have a strong information theoretic bias. This is basically, there are very powerful reasons to believe that counting bits and counting information is really the correct way to understand, well, I mean, correct way to interpret information, right? And I say this because some people really don't like it, right? Some people, they suggest other metrics, other measures, other approaches, other possibilities. And my retort is basically bunk them. This just means you don't have the correct theoretical framework in place to understand what's actually happening. If you don't have a way of measuring information content, you don't really have a model of the interaction. All right, more about experimental results, some basic definitions. The study of pairs is going to be the study of matrices. A word pair data set is a matrix. Rows and columns are left and right words in the pair. It's a sparse matrix. Most word pairs are never observed. There are some global properties, a collection of numbers that characterize the general shape. Okay, I'm going to start with the logarithm width and height. Everything is a log because that puts everything on the same scale. It basically makes everything comparable. Everything gets measured in bits, so the log is going to be base 2. Left and right are not equal for mundane reasons, at least the word pairs, right? The word the never appears at the end of sentences. Punctuation marks don't appear at the start of sentences. You know, the matrix is not quite a square matrix. Interesting numbers include the number of non-zero entries, the total number of observations. It's handy to express these in a relative fashion relative to the size of the matrix. This just provides better intuition. And so here I introduce sparsity, which is the fraction of non-zero entries, and rarity, which experimentally appears to be independent of the data set size. Entropy, yeah, well, okay, entropy is not that interesting, but it's conventional to report it. Basically, if I'm going to be information theoretic and stay true to my beliefs, this is obligatory to report. There's a marginal entropy with left and right, written in the left and right margins. It's written in the margins, right? That's why it's called marginal, right? There's also a total MI, which is a sum and difference of these things, total mutual information. Right? Okay, look, okay. This slide is going to put it, you know, is going to be painful for you to look at, so I will try to be as quick as I can, and I apologize in advance. There's a small data set on the left, 1,000 by 1,000, sorry, 100,000 by 100,000 words versus 500,000 by 500,000 on the right. This is not a large language model. This fits on conventional desktops. It's about 1 million times smaller than Google's large language models. Okay, that's 6 orders of magnitude smaller. If you scan the line marked B, you'll see there's up to 50 million non-zero entries in this thing. The sparsity varies. Sparsity is a fraction. It varies from about 1 in 1,000 to maybe 1 in 4,000 of the pairs that are non-empty, right? That are observed out of all possible word pairs. As few as 1 in 4,000 are actually seen. This is the driver of software development. You have to have a way of representing sparse data in your system. Pretty much all conventional math and probability frameworks just don't support this. This is a software roadblock. The rarity, the middle row there, really does appear to be independent of data set size. I think this is meaningful. I don't yet know what it means. The next row just shows, as you increase the number of observations, then total observations per entry grows as well. So that makes sense. Total entropy grows slightly. In the last row, the total mutual information stays constant or maybe even drops a little bit. Hard to say. As the data set size increases, it's not large. There's not a lot of data in word pairs. Okay. Think of the mutual information as a measure of the amplification. This is sort of a key point here, is think of it as an amplification of the information that I have. Given some data set, it tells you how much information you were able to collect up and concentrate. Now here I have 1.5 bits of information that I've gained. Okay, so this feels laughably tiny, right? But it's positive, it's greater than 0. You can actually extract information. We'll do better shortly. Let's see, a short aside on sample size effects. The vertex degree is a classic statistic from the early days of the study of large graphs, which tended to be scale-free graphs with preferential attachment. I don't really think that's a useful way of thinking about the present case, but I've found that reviewers just sort of clamor for this kind of stuff because all of the classical papers talk about it. So here it is. The graph is Zipfian. I have no real intuition or theoretical explanation why the exponent or the slope is 1.6. I want to bring your attention to the top left side. At the top of the chart, these are the words that occur in only a handful of pairs. When I look at the data set, it reveals that it's mostly junk. Bad punctuation, it's typos, it's bad quote segmentation, it's stray HTML markup. So basically, if a typo occurs only once, then yes, it will be in only very few word pairs, which translates to having a vertex with a very low degree. Right? And the degree is just the number of other vertices that it can connect to. Amazingly, almost 2/3 of the data set consists of this kind of junk. Right? This eats up RAM, this eats up storage. Data set trimming is not a bad idea. Right? At the bottom, far bottom right, it's actually off the graph. Far bottom right of the graph would be the word the and any sort of punctuation. The word the and punctuation can occur in a vast number of word pairs, and so they have a very large degree. All right. I rather like this one. This is the distribution of the mutual information of word pairs. 28 million word pairs. So again, this is absolutely microscopic compared to large language models. The distribution breaks down into the sum of two curves. And it's almost perfectly the sum of these two curves. And I find this alone to be really quite amazing. One is Gaussian, centered roughly at 0. The other one is a log normal curve. I've never seen this discussed anywhere before, so I don't know of any theory for it. I can offer a simple explanation. The Gaussian is centered at 0 is entirely due to random sampling effects. It's what you'd get if you just took a bag of words and randomly sample 2 with replacement out of that bag. It's classic analytic combinatorics. The result is a Gaussian centered about a mutual information of 0. The rest, the log normal curve, is presumably meaningful English language correlation. The problem, of course, is in the middle. How do you tell which is which? Well, above you have above a mutual information of about 10. It really is English. Between 2 and 10, it's what? It might, given word pair, it might be random junk, it might be English. I don't know. This, by the way, you get, if you do this for Mandarin Chinese, you get an identical graph. It's well, more or less identical. It really has the same shape. It splits out into these two pieces quite cleanly. It's I suspect you'll see this for just about any language. Okay. Again, stuff you already know, but I just have to repeat it. I wish, that I was hoping the audience would be a little bit bigger here, but maximum spanning tree parsing. This is a 25-year-old idea. Here you're just going to take a sentence, you're going to consider all possible spanning trees on the sentence and pick the one with the highest total mutual information. The innovation here is the jigsaws, right? You take each edge, cut it in half, label the endpoints. This results in a word with some connectors on it. This is the jigsaw. Elsewhere, these get called disjuncts. Today, I'm just, right, I mean, they're called disjuncts because they get disjoined from other occurrences. I'm still fishing for a good vocabulary for this stuff. My favorite for today is jigsaw, so I'm going to try to stick to jigsaws. Anyway, the idea is you count these, right? You do a MST parse of a large number of sentences and just count how often you see each jigsaw piece. This gives you another set of pairs, right? This time it's pairs of words and jigsaw and connector sequences. So columns of this matrix are going to be the words, the rows are going to be different connector sequences. The matrix is rectangular. How should I say it? It's very rectangular. It's about 10 times wider than it is tall, right? There are 10 times more connector sequences than there are words, roughly. Another graph. Okay, I'm going to skip this page entirely, right? This just shows what happens when you trim away infrequent pairs, right? So trim away words that you've seen only twice or seen less than 5 times or 10 times. Trim away any matrix entries that are seen only once or twice. This will strongly shrink the data set size. This trims away all the junk, all the typos in the data set. You do have to be careful. There are geographical place names that are used only a few times. There's product names, given names that are used only a few times. Foreign language loanwords that are used only a few times. So trimming is dangerous. It does reduce the data set size. And if you look at the last row, trimming does lower the overall mutual information gain. All right. And really the only takeaway from this crazy table is that the total mutual information is much larger than it is for word pairs. Right? MI of 9, or even 6 is much larger than the 1.5 we saw before. We've seen significant amplification gain. This is actually not unusual. In radio electronics, the very first transistor after an antenna has a gain of about 2 or 3, right? So that's comparable. That's about what we saw as the gain for the word pairs. The next stage of a radio amplifier can have a gain of 100 or 1,000, and that's more or less what we're seeing here. This seems to be real amplification, and it seems to be in the same kind of ballpark you'd see for radio electronics. So I just find, I'm sort of thrilled by that. I think that's kind of neat. All right, this is a boring slide. All right, I'm gonna graph the mutual information for the jigsaws, same as before. This time it looks messy. I don't really know what's going on here. The meaning is opaque. It's a bit of a mess. The different curves here, they're for different trimming levels. The more you trim, the closer it gets to Gaussian. Yeah, but I don't find this particularly satisfying anyway. This graph, though, well, you're right. This is the earlier graph that I showed. This really does surprise me. I mean, it's just a wow graph for me. here's what it really means. Here's what we're really looking at. Let me define an inner product. It is, well, it's the inner product. It's the probability. I'm summing over the connector sequences here, D. The inner product all by its naked self is not really appropriate because probability space is not Euclidean space. Okay? Euclidean space is invariant under rotations. Inner products are invariant under rotations. Probability space is invariant, or rather covariant under Markov chains. These are two very different beasts. So really what you want to do is you want to take the mutual information of the inner product. This time the mutual information is symmetric. It does correspond to the conventional textbook definition. In practical use, there's a problem with IMI. The highest mutual information pairs, well, they're also very infrequent. And so it'd be nicer to have something that weights frequent pairs more heavily so that the commonly observed pairs rise to the top. So I've defined a variation of information, right, with a square root in the denominator there. It seems to strike a happy medium between picking frequent pairs and picking high information content pairs. The Gaussian curve that I graphed, it comes out Gaussian whether I graph the MI or the VI. Right? It's almost completely untouched. It just gets shifted to the right. And this is actually kind of remarkable because the rankings are utterly different between the two cases. The correlation between these two measures is low, and yet you get Gaussians either way. You can play the similarity game with other kinds of metrics. There's an assortment, a rainbow of guitar distances you can define. These seem to work quite well. The cosine distance is terrible. It's absolutely terrible. But again, this is probability space is not Euclidean, so this shouldn't be a surprise. Yeah. I don't know, it might not be clear how I'm making this claim. This is kind of a subjective claim. Basically, you sit down and you just eyeball the kinds of words that are judged to be similar by all these various metrics, and then you look to see how, how good does that look, but you can do this at home, right? This is easy to replicate. Cosine distance just, it claims that things are similar when you look at them and it's pretty clear that they are not. All right, well, I've already talked about the spin glasses. What more can I add here? Each axis of the space is a word. The dimension of the space is equal to the size of the vocabulary. The vectors here, the word vectors here, have coefficients given by the mutual information. And again, just why is this remarkable? This says the grammatical use of words in the English language, right? The syntax and the grammar of English is uniformly distributed in the space of syntactic relationships, right? The English language leverages the syntax to the highest possible degree. It's maximizing the utility of syntax. Right, so somehow we, as humans, as speakers, we use grammar, right? I mean, we use grammar and we say use syntax to communicate ideas, right? English uses syntax in a maximal way. Of all the possible ways it could have been used, all the possibilities are used equally. And I don't want to bias this too much towards English. I suspect that all human languages behave this way. It's just that, English is all that I have results for right now. Here's some typical results. Nothing particularly surprising here. I'm just going to return from the atmospheric heights and just show. Yeah, and in real life, if you like doing your laundry, you see stuff like this. These are the top ranked clusters ranked by the VI similarity I mentioned earlier. I can't really measure, I don't know how to measure the quality of these scientifically, but gut sense, you look at this table and you say, yeah, that looks like a pretty good clustering. It's what you would expect. Emphasize here what? This is similarity in grammatical usage. This is similarity in the way words appear in grammatical context. This is what the jigsaws are doing. Again, jigsaws, they're kind of like n-grams, they're kind of like skipgrams, except they provide explicit grammatical relationships, which skipgrams do not. They go out not only to the neighboring words, but the neighboring words reflexively come back. Right? In skipgrams, the relationship is always a sort of one way. It's a word in a context. In grammar, the relationship is back and forth. It's a two-way relationship. Right? So when you say the subject of verb, well, it's symmetrically the verb subject. Right? Both parts agree as to what their role is in a sentence. In grammar, one part is not ignorant of the other the way that they are in skipgrams. So this is a grammatical result. All right, we're coming to the end here. Some quick notes on word sense disambiguation. Any given word can have multiple senses. One has to be able to tell them apart. Grammatically, different word senses appear to be associated with different grammatical patterns. Here we, since we're dealing with linear algebra, these are just linear combinations. I've been experimenting with algorithms to hold them apart. I've said this before, I'll just say it again. Conventional clustering algorithms, such as agglomerative clustering or k-means clustering, they just completely fail on this task. And it's not that this is a hard task, it's just that researchers have never really dealt with disentangling high-dimensional linear combinations before. There doesn't seem to be any literature on this topic, and so I've sort of had to roll my own here. The effective technique seems to involve, let me just completely, it's politically charged, right? It seems to involve democratic voting to admit members into an exclusive club of shared interest, right? Each existing member of the club gets a vote. The vote is based on how similar the existing member is to the candidate. Right, and here by similar, I do mean vector similarity. How exclusive should the club be? If you lower the barrier to entry, the club grows. At first, it's going to grow slowly, but then it takes off at some point. It grows explosively. Right? I claim the ideal size for a club would be the knee of that curve, just before the explosive growth takes off. Okay, what defines a club? A club is the shared common interests. Right? In this case, the shared common interests are the shared jigsaw connector sequences that all the club members have in common. If a club member has interests outside of that club, well, those correspond to a different word sense. Right? Those jigsaw connector sequences should be assigned to some other club or club. So clustering in this way accomplishes two things at once. It generalizes from the specific to the general, right? Because that's what clustering does. But it also filters out all of the exceptions, which clearly distinguishes and disambiguates the different grammatical roles. Nothing fancy here. It's just not something that you find in off-the-shelf software, nor do you find in the academic literature. Beats me why. All right, well, the conclusion. So what have I been beating on here, right? Information theoretic explanations are paramount. Don't assume anything if the experiment doesn't support it, right? Don't do theory in the wild. Structure can be extracted from undifferentiated samples taken from nature. Structure is a synonym for grammar, right? It means the same thing. It's expressed as grammar. And this whole process is recursive. I didn't really show the recursive process, but basically once you have a uniformly distributed pattern, you can then ask how a given case differs from that uniform distribution. This is an act of searching for differences from the mean, and extracting the symbolic structure from the differences, and using this to define a new, uniformity at the next level. And so you can now repeat this process. You can lever your way up the ladder from rung to rung to get, move upwards in the semantic direction. So this is a combined theoretical and experimental program. If I had a larger audience, I'd invite everyone to participate. In this small audience, I think you all are already participating, so I don't know what to say. So I guess that's the talk. I'm gonna halt the screen share. Now, with some luck, you'll see my face. Or maybe not.
So Linus,
You can't see me.
yeah, well, we can see you, but we have some questions for you. Are you ready to take them?
I'm ready to take all questions.
Okay, so there is a question from Nikolai Mikhailovsky. Am I taking your data right? Am I taking your data right? It takes about 10 bits to encode a word in your datasets.
No, if my vocabulary is 100,000, then it takes me log 2 of 100,000 to encode it. So it takes 16, 17, 18 bits.
Basically, sorry to interrupt. Typically, in an English text, it takes about 7.5 bits to encode a word, or about 1.75 bits to encode a letter. That's based on the entropy estimates getting back to Brown of 92. Your data on your set's entropy shows significantly higher entropy, if I'm not mistaken. So I just want to figure out how different your texts are from the standard corpora.
All of these texts are taken from the almost all of them are taken from Project Gutenberg. There's some fan fiction in there as well. Why are you not seeing a pretty picture of me? I don't know. But yeah, it's all fan fiction. I don't quite understand what you're saying. I mean, certainly you can do compression tricks of various sorts, but look, I mean, if you got 100,000 words, you have 100,000 words. You got to be able to tell them apart.
It's a little bit more complicated than that. Sorry to interrupt you. And the question of text entropy dates back to von Neumann, Kolmogorov, and have been estimated by, I think, von Neumann as well. And the English text estimates on a Brown corpus of million words done in 92 give top estimate of English text entropy at 1.75 bit per letter, or about 7.5 bits per word. So
I have no idea what that means. I mean, if you have 100,000 words, you have 100,000 words. You're
of
not
course,
gonna,
but they are not independent. The big problem is the words are not coming in arbitrary. They are like independence assumption is not true for language.
Well, right, that's what my whole talk is about. It's how you fish out
Yes.
how you fish out dependencies. This is how you go about
Yes.
actually
So
obtaining them.
I'm just trying to figure out how your experimental results can be compared to any other experimental results out there for tens of years.
I don't know that there are any comparable experimental results out there. I mean, I don't know anybody else who has done
of course, most of what you said is very interesting and quite unique, but things like entropy is entropy, like it's pretty straightforward.
Yes.
So if the entropy of a text is different from typical English text, there's something different in either the text or the way you measure.
I didn't measure the entropy of the text. The entropies I presented there were the entropies for word pairs, for the word pair data set. This is not the text. This is just for word. In the first case, it was just for the word pairs. In the second case, it was for the word connector sequence pairs. So it's no longer text, right? The text has been discarded and thrown away. All that's left in the data set in the first data set are the pairs, and in the second data set, the the jigsaws.
Okay, gotcha. Thank you.
The solution.
That's correct. Big rounds should have higher entropy than the text itself. That's true. Makes sense. Thank
Nikolai,
you.
And what about your second question about distribution?
Yeah, so I was looking at this marvelous distribution that's a combination of Gaussian distribution and whatever. If we can back to that slide.
I'm sorry, which slide?
With some kind of distribution that's a combination of Gaussian distribution and something else.
Yes, that was for the word pairs. Let me find it. Here it is. Let me attempt screen share. My browser is preventing access to my share screen. Why is it?
No worries, but the key question is.
It's also preventing my video.
No worries. So the question is, have you tried to compute the same distribution on some kind of standard corpus, like Brown?
I don't have access to the Brown corpus.
Well,
I'm certain it'll be this. I'm certain it'll be almost identical. I've done this for Chinese. I've done this for a few other languages. This seems to be language independent. It seems to be corpus independent.
Any publicly available corpus.
Last time I looked, the Brown corpus cost $10,000, and $10,000 was more than I was willing to pay.
Well, okay, discard Brown. Any publicly available corpus.
Yeah. Sure, point me at one, I'll use it, right? Just don't point me at Wikipedia.
Okay, I will.
Okay, thank you, Nikolai. And Linus, by the way, let me know if you need the link to Brown corpus. I use it in the study that I will be presenting later today. So I have got some more questions to you, Linus. So first of all, you was talking about different clusterization approaches like Jacquard, similarity, cosine, and different metrics that you can use for clustering. And also, I believe you have some other parameters that may lead you to have different categories learned. So have you thought about somehow assessing the quality of your clustering or grammatical categories learned, like comparing your clusters of words against some known grammatical categories like synonyms or parts of speech to ensure to actually validate the quality of your study against these existing categories? What do you think on this?
Basically, what I find is the existing categories are terrible, right? I mean, you start looking at what people have done by hand and it's crappy data, right? This is one reason why you want to get away from that sort of stuff, because as soon as you get the curated stuff which people have created by hand and you start comparing the machine learning to it, you find the machine learning surpasses the quality of the hand curated materials. And so the comparison becomes very difficult. Okay. A few years ago, this is why I kind of went on and on about creating synthetic languages on the internet discussions there, was because at least for a synthetic language, you know what the frequencies are, you know what the distributions are, you created some random artificial language, and now you can create a corpus from it. And so the question becomes, can you reverse engineer that and come back with the original language that had been randomly created? That would be the proper way of doing it. I tried that for a while. It turns out to be really hard. It turns, well, there's two things. One is eyeballing becomes really hard, which means debugging becomes really hard. The other issue is you can have multiple synthetic grammars, multiple artificial grammars that yield exactly the same language. So you can start with one grammar, create a corpus from it, learn a grammar from it. The learned grammar is completely different, but when you generate a corpus with it, you find out that it generates exactly the same corpus. So this is not a one-to-one mapping, right? You can have multiple grammars describing the same corpus. It's not unique. But if you really wanted to be scientific and measure things exactly, that would be the way to do it, because now you can control all aspects of the grammar.
Okay. And another question, just for reference, I believe in some earlier work that you have done for the tokenization, you was using some rule-based or hard-coded tokenizer. So the grammar learning starts after you have done all the tokenization stuff and separating periods, colons, semicolons, and commas from the words. So what is your current approach to tokenization?
My current approach is I'm actually planning to start focusing on it a lot more. I mean, it hasn't changed from what we talked about, from what you just described, but you've sort of convinced me that maybe I should go back and look at it a lot more carefully. And the tokenization there would be what I did in the lightning part of the talk. And that's to say, okay, let's go ahead and create these random filter sequences, right? Let's go create the wavelets, slap those wavelets onto sequences of letters, right? You don't have to do this for sound. You can just slap them onto sequences of letters and see what kind of tokenization comes out of it. Right. And then here the goal would be to do it not just for letters, but to make the software generic enough so that I can also do this for sound. I can also do this for video. But certainly starting with letter sequences is much easier.
Yeah. Okay. Thank you. I think we'll have some talk about this after the next talk about the tokenization stuff. And finally, there is a comment from the YouTube. Roscoe Hillenkoeter is saying that I call these groups that you are describing semantic spheres, with the idea that one people that interact with another have shared meanings, and so these shared meanings are getting in the common semantic spheres. Any comments on this?
I didn't quite understand. I didn't quite understand what the comment was. Semantic spheres?
Yeah.
Yeah, I have no comment because I didn't entirely understand it.
Okay.
Is this in the chat window?
I think then we can move along. So thank you, Linus, very much for your presentation. lightning and encouraging, and then Nikolai Mikhailovsky can present his considerations on the same matter. Nikolai, please go ahead with your slide.
Before Nikolai continues, I'm going to drop out and drop back in simply because I want to make my video try to work.
Okay.
Hello, everyone. Can you see my screen?
Yes.
Okay, so I'm Nick Mikhailovsky of NTR Labs and Tom State University, and let me share with you some thoughts on unsupervised learning of linear grammar-based language models. So let me first tell you why at all I'm looking at all these. And the key is the language models, because language models are models that assign probabilities to sequences of words. And in the recent world, any linguistic task is assisted by large language model. Like you take bird, you build a task-specific head with task-specific loss, and you just solve your computational linguistic problem. But, oh, sorry, there are some problems with current language models. The key problem is that correlation in text decrease according to the power law. And that's considered to be an outcome of hierarchical structure of human texts. There are various ways to measure that, but overall, the hierarchy that's natural to long human-generated text is the source of power law dependencies. Actually, yet another way of looking that is indeed spin glasses, and I was like super excited to see Linas mention the same thing today. But if we take like a probabilistic regular grammar or Markov chain, the mutual information will decrease exponentially with the distance between symbols. So to have a power law decay of mutual information between symbols in a text, we need to have a kind of context-free grammar or some equivalent structure. And although the strict mathematical results that have been proved relate to Markov chains, it looks like large language models based on neural networks also exhibit Markovian behavior. Actually, generating long text with even large models like GPT-2 requires tricks that are pure engineering and do not rely on language models. For example, continuing something with a GPT without special sampling leads to cycling the model, which obviously like exponential or zero more than exponential decay of the mutual information. And actually, it has been shown that very recently, that's July work from Google, that indeed transformers exhibit Markov behavior on a number of tasks. So it would be interesting to build language models exhibiting at least hierarchical context-free grammar type behavior. And that would be a move into the right direction even though that may be not enough, because it's long known that natural languages cannot be described by a context-free grammar, because natural languages are either Turing complete or at least require a context-dependent grammar. So that's the viewpoint I'm looking at linked grammars and linked grammar-based language models. Actually, linked grammar-based language models are not new, and they have been considered by Slater and Temperley in their early works prior to the Gisgoth type parse trees they have introduced a year later. But it would be nice to see what needs to be done to the current discourse on that to really induce a linked grammar-based language model from a corpora. So one problem that prevents the current formalism of linked grammar from being translated into a language model is the problem of loose connectors. Actually, if a word has a certain set of connections when we build a language model, that's like division by zero. So we need to introduce termination tags for any type of connection, not just start of sentence that's in typical formalism that's used, for example, by Linas. To see how that works, let's see how we can generate text with a statistical linked grammar. Suppose we have a lexicon of terms and their respective disjuncts, and we have probabilities of words that would plug into that connection, including terminal tags. And let's assume that the probability of the term plugged into the disjunct depends only on the original term and the connector. That's a very strong assumption, and as we will later see, it's not true. But to construct a formalism for language models, we can go with that. So let's start with a word, and this word can have a disjunct that have two words to plug in with different probabilities. We may have some probabilistic sampling method, and it can sample one of these words. Now we can go to the other disjunct, sample other words here, do a probabilistic sampling, and then finally we build, thus one by one, we can build a sentence or some utterance from the starting word with a pretty mild assumption on the probabilities. This will be a finite process almost always, and we will have finite sentences generated this way. This can be described. This process can be described by a frequentist statistics model that's based on counts of the respective links, disjuncts, and terms, with obvious constraints like probabilities summing up to 0. But at this point, it's important to look at how the things work for older types of n-gram models. Because in any language model, we want to estimate the probability not only of a certain word, but of an utterance as a whole. A typical approach to that is applying chain rule, and for n-grams that are linear, that's very straightforward. We apply chain rule and get a probability of utterance. If we take n-grams, that approximates a probability of an utterance in naive Bayesian way. Actually, it's super important to understand how exactly n-grams are approximating the probability of an utterance. Basically, the right part of this formula is an n-gram model, but the left part describes the context of each n-gram. And this thing can be summarized into the probability of the context in which n-grams operate. And this approximation by n-grams means that this context considered to be equal to 1, this probability of the context. There's an explanation why can that be done. And the explanation is the following. If we have a large corpus and a long sequence of symbols or words, both counts actually exist in that, but the counts are equal to 1. So the probability of this context in this context is 1. And that significantly relies on the assumption that we work with long text. With a short context, that's exactly not true. In a corpus, there will be a lot of short context, but looking at a long context, it's just 1. That's super important. When we estimate a probability of an utterance with a lean grammar-based language model or any tree-type language model, we work with graphs and can actually build a tree of a sentence of an utterance. The context information overall is beyond the sentence or utterance. Like, consider Shakespeare's play. Any utterance of Hamlet or any hero is in context of all the play. And typically the context is beyond. With n-gram models, the context is prior to the n-gram and is implicitly considered as we have just described. With the tree-like models, we need to take the context information somehow explicitly. We can start with the root of the tree and use the chain rule along each branch. But we should specifically take context into consideration. We can take the formalism for the chain rule from the probabilistic graphs and denote W1, the root word of the sentence tree, WK at any term appearing in the sentence And this is not a division, that's a denotation for the path from the root of the tree to the term. And we'll denote Wk minus the immediate predecessor of Wk on this route. So, I'm sorry. So with this notation, we can write the probability of a sentence or an utterance as multiple of all the conditional probabilities of word conditioned on a tree from the root to the word. The typical, in a sentence, the typical path from the root to the word is not long. It's like maybe 3 or 4, maybe 5 words, but typically not much than that. Let's compare that to Uret formula from his PhD thesis, 98. He assumes that the probability of a word depends only on the word and the word linked. But as we have just seen, that's a simplification. That's a significant simplification because this probability depends not on the word linked, but on the other parts of context, both in sentence and out of sentence. So how correct is this Uret approximation? I hope that it's not. If we move to the convenient word of n-grams, this approximation says that a probability of n-gram is equal to the probability of its final b-gram, which is simply not true. So the Uret conclusion that entropy of the model is completely determined by the mutual information captured in syntactic relations is incorrect. It's not like a super big problem. He concludes that the goal of the processor is to find the dependency structure that assigns a given sentence a high probability, basically language model. In chapter 3, I showed that the probability of a sentence is determined by the mutual information captured in syntactic relations. Thus, the problem is to find the dependency structures with the highest total mutual information. Based on the above, I declare that this conclusion is wrong because it ignores in-sentence information. When we have discussed the chain rule approximation by n-grams, the key to this approximation was the context is typically very long, and the probability of this context can be taken to be 1. Within a sentence, the chains are very short. As we said, it's maybe 5 links from any word in a sentence to a root. Thus, this type of approximation is not true for that. And this naive Bayesian assumption cannot be used to compute reliably compute the syntactic structure. We need to somehow take the context problem into our computing. What needs to be done and what we need to actually work on if we want to learn language model, like any tree-type language models in unsupervised way, is to take into account the effects of the context, the text non-stationarity, and other important properties. So basically that's it from my side.
Thank you, Nikolai. Does anyone? Okay, so Linus is commenting that the whole point of the jigsaws is that they overcome what is wrong with the MST parsers. Most MST parsers are MIDI-core for that reason described. Linus, can you elaborate on this in the context of Nikolai's presentation?
Well, Linus, I think we can't hear you. You have turned off your mic.
Let me see if we can last. Linus?
I think Linus froze.
I'm trying to figure out which of the two Linuses is. Okay, now Linus, I think we hear you now. Linus? Okay, something is going on there.
Sorry, Linus, I didn't want to do that to you.
Okay, so Nikolai, can you comment on what Linus has said on that jigsaws versus MST parsers?
Well, it's a little bit complicated for me to completely understand what's there, but for me, the jigsaws are just another way of linking just two words. And if, however, we connect, when we still work with a couple of words, we will still have the problem of context. We need to work with longer sequences than two words.
Okay, I see. So Nikolai, I think your interpretation of jigsaws is not quite correct, because the jigsaws, in my view of Linus's theory, are corresponding to disjuncts. And in disjunct, you have multiple links connecting the word to some words, part of which may be adjacent, and some of which might be further away from the word. So like, for example, if you have transitive verb, like I like beer, then the verb like has two links to subject and object, and it's kind of it's what Linus calls jigsaw. So there are two links coming in outside direction, and you need to consider these parts, this pair of links, as a unit. Okay, and some more complex grammatical structures are corresponding to more links coming out from the lexical entry. So the grammatical unit becomes not an n-gram in the common sense of n-gram, where you have the sequence of adjacent words in the form of linked list, but it's kind of the graph structure which connects words that might be adjacent or residing further away from each other. And the main problem that I see here is that in order to learn grammar from these disjuncts, for jigsaw pieces, you need to find them somehow. With n-grams, it's pretty simple because you just cut the text using some sliding window into n-grams, overlapping n-grams, and then just do some probabilistic modeling with all these condition probabilities, as I will be talking on the next talk. But with jigsaw puzzles or disjuncts, when you have some text to run unsupervised learning on it, you cannot do you don't have these n-grams. You need to generate all possible combinations, and in order to generate all these possible combinations, you need somehow to reduce the complexity, and mutual information, pairwise mutual information is a way to reduce this complexity.
Let me probably my frequent references to so familiar n-grams is somehow misleading. So let me just get back to a few things in what I have been saying. Lin grammar generates, let's say, a colored graph of an utterance. We can, we have, it's not even a colored graph, it's a colored tree. There's a root, and there are links from some words to other words, one to one, building a tree that's colored. Like these jigsaw puzzles is just coloring of a tree edges. That's just a little bit different wording, but it's in some parts of math it's more common, but it doesn't matter. So in a Lin grammar we have a tree, and we go and if we want to build a language model, we want to compute the probability of this tree. So we have a probability of this utterance. So if we want, if we go, how do we compute a probability of a tree? We need to compute the probability of all its branches from the root to the end of each branch. Now the probability of the branch depends on all the branch, which can be like typically a few links, like 1 to 5, like normally. URET says the probability only depends on 2 parts of the link, but that's not enough, because the branch can be just a little bit longer, not just 2 vertices, but it may be 3 vertices, it may be 6 vertices, not much more, but still it's a small number, so that we cannot reduce its probability to 1 as we do with n-grams. But it's non-zero number often. So if we compute mutual informations based on only pairs, we compute wrong probability of a graph. And if we compute wrong probability of a graph, we cannot compute a correct language model, and then the structure will fail. That's just overall model of what's happening out there.
Okay, thank you. There are a few more comments from Linas. So the comments are: random word pairs are random. They are mostly junk. I think that's in agreement with what Nikolai you are saying. Random jigsaws are mostly junk. They are random from low quality of MST parsers. I would also agree. Then the goal is to start with low quality MST parsers and count to find which ones are actually common. Well, that's inspiring, but then the question is how good we can do that. Then next comment from Linas. So yes, the base assumption of working with n-grams is wrong. The goal is to amplify away from n-grams with counting. Okay, and yes, the sampling I uses is a uniform distribution of all possible trees. The whole talk, my whole talk was about how to do that. Okay, so thank you, Linus. So Nikolai, you are saying that, but a successful approach should in a proper way take into account the effects of the context. So do you have any ideas of how we actually formalize the context?
Not really yet. It's let's say it's work in progress. I will be happy to discuss that. At the moment, there's some indication of how may a context be used in a very simple way for n-grams model, but that's kind of memory type things. But that's very early to describe that, but I'm happy to discuss that at any time.
Okay, and there is a new comment from Linus, but I talked about how to formalize the context, how to do that thing you are doubtful about. So it looks like we need to rewatch the Linus's talk in order to figure out how he suggests to formalize the context. Linus, before we move on the next talk, do you have a chance to jump in and maybe clarify on this context specification part by your voice? Linus, we don't hear you. Linus,
Not really. We cannot.
We cannot hear you, unfortunately. Well, so let's work on sorting out how we formalize context a little
Oh, wait,
bit.
how about now? Now can you hear me?
Yeah, you are with us.
Well, that was difficult. Boy, I don't know where to start. I mean, half of what you said is exactly right. I mean, the whole point is that the n-gram approach and that those assumptions about uniformity, all those things you said were correct, but the whole point of counting the disjuncts was to move past all of that, right? Any individual parse is just going to be low quality. It's not going to look very good. It's you know, you're at, you know, picked out some great examples, but most of them are not that wonderful. And so now the question is, how do you amplify the thing? And my claim was that you amplify the thing by taking many such parses and averaging over them. The way that you average over them is you cut them up into those pieces and count the pieces. This gives you a brand new grammar that's not, it looks like n-grams, but it's not n-grams anymore. It's a distillation of the original set of n-grams into a new set of n-grams that is, you know, that I claim basically is much more accurate than the initial ones that you started with.
Probably we need a separate discussion of that, because I probably don't quite get the whole picture. But back then, like 30 years ago, there were works on grammatical n-grams. And I believe Jelinek and probably somebody other have some works on grammatical n-grams. They have used parts of speech and they used corpora manually tagged. So that's definitely not the unsupervised learning and definitely like some human type of grammar, but probably it makes sense to get back to these works, take a look at how do they do that in a supervised way and try to translate to unsupervised.
Okay, so we're actually running out of time. So Linus, let me ask you a final question to make sure I understand what you just have said. So are you saying that, so let me put it that way. So here is the way we were doing the grammar learning in the few years ago in the project that we run with Alexey Glushenko and Oleg Baskov, you know that, and the results that was presented last year. So what we were doing the MST parsing using mutual information pairwise. And then after doing the MST parsing, we were trying to learn the grammar based on the MST parsers. And it didn't work quite well, as you know. So am I right that you are suggesting, instead of doing what we did, generate all possible parsers for every sentence, get all possible jigsaw puzzles or disjuncts or whatever, and count this. So instead of doing mutual information counting pairwise, do frequency counting on these jigsaw puzzles or disjuncts, and then do all further grammar inference based on these disjuncts instead of doing it based on the connectors. Is that what you are suggesting?
Sort of, right? I mean, if you, there's a disconnect here and I'm trying to figure out how to explain it, right? You can certainly start with all possible uniformly distributed trees on a sentence. But if you start with that, you won't get any sort of amplification because you gave equal weighting to each and every possible tree. What you really want to do is you want to say, no, some trees are more likely than others. And the URIT stuff tells you which trees are more likely. But now that you know which trees are more likely, you have to you have to repeat that same step a second time, this time weighting each tree appropriately. Right, so you basically have to turn the crank one more time. Turning the crank once is not enough. You have to turn the crank twice, and that's where the amplification comes from.
Okay, thank you. At least I get the idea. So we need to move ahead. So Nikolai, thank you for presentation, and Linus, thank you for discussion. Now we need to dive a little bit deeper to the level of words. And let me show my slides. It's my turn to speak out. So do you see my screen?
Yep.
Okay, let me view the screen, enter full screen. Okay, so I'm going to talk about the unsupervised learning for lexicon and punctuation. And the motivation, but before we actually run for the presentation, I would like to entertain you with this puzzle. So here is the puzzle. You see 3 languages here. Language 1 is in the top row, language 2 is in the second row, and language 3 is in the bottom row. So each of the rows corresponds to different representations of some language is in some space. I will give some details later what are these representations. But the question is, just from the look and feel of these pictures, try to guess which language is English, which language is Russian, and which language is Chinese. So 1, 2, and 3. one language is English, another language is Chinese, and another language is Russian. So just take few seconds, take a piece of paper and write down where is English, where is Russian, and where is Chinese. Giving you 10 seconds and we go ahead. Okay, so the answer will come out in the end of this talk. So the idea of the work that I will be presenting is provide the ground support for lexicon discovery, punctuation discovery, and tokenization in the end, in order to formalize any language grammar in forms of what we call deep patterns. And deep patterns mean that every language model can be represented in form of a semantic graph, where each vertex on each graph corresponds to either word or meaning or some grammatical category or some ordered structure encompassing some grammatical patterns like transitive verb pattern, non-transitive verb pattern, and also these structures may be interconnected with some disjunctive or conjunctive rules or associations, like we can have lemmas for synonyms, or we can have lemmas for or disjunctions for possible use of different grammatical constructions to encompass the same kind of meaning. And in fact, it gets down that from words at the very bottom and to abstract concepts, grammatical categories, and linguistic patterns at the top, you have kind of hierarchical structure. And this hierarchical tree of or forest, or actually forest of hierarchical structures from the words to high-level concepts actually represents the language model. But in order to solve this task, in order to talk about the words and grammars, we need to find these words in the conventional continuous speech or in conventional continuous text. And in the project that we have run based on the Linas's groundworks a couple of years ago, the problem that we have found is that, well, we want to do the unsupervised, so to speak, grammar learning, but then if we are going to have completely unsupervised learning, that we should also have unsupervised tokenization. And that was not part of our work because we were using rule-based handmade tokenization, which was doing a lot of dirty tricks in order to figure out individual words and tokens and punctuation marks that can be further bundled into that process of building the MST parsers and the further formation of the grammatical rules in form of link grammar. So, and the motivation of the presented work is that try to fill this gap with completely unsupervised tokenization process before moving to completely unsupervised grammar learning process. And another motivation of this work is that when we were doing that grammar learning based on the mutual information, we have found that the quality of the parsers were pretty, unsupervisedly learned MST parsers were pretty low. And there was some idea to look for other measures that we can, or other metrics beyond mutual information that we can use in order to learn grammatical structures. So these are the two major motivations in this work. And by the way, there is a first motivation at the top of the slide. We believe that some cognitive processes specific to language processing are common in terms of dealing with any sequential, any sequential processes and activities. So we believe that being able to segment or cluster sequences of symbols is at the bottom some deep layer of the cognitive processes is the same with segmenting or structuring any experiential environments or experiential situations, like playing games, learning some physical activities, learning some I don't know any skills that involve different processes with different actions that have to be executed in specific sequences. So what we have started with on this tokenization and text segmentation work were 2 papers. And in both of these papers that I reference here, the researchers are trying to come up with the framework so they can learn the rules of the text segmentation. And when you segment the text effectively, you figure out the pieces of text that are framed with the boundaries of the segments, and these pieces of text are corresponding to either words or punctuation marks. So in these 2 researches, the different approaches for this were considered, and few approaches were based on the same heuristics or mathematical models of mutual information and conditional probability that Nikolai and Linas are describing in their work. But one of the approaches in the second paper was quite interesting because it was introducing the notion of the transition freedom. In the work they call it freedom of transition, but in further discussion we refer to it as transition freedom for simplicity. And the transition freedom can be explained in the picture on the top. Like, for example, there is a word passed by a sequence of symbols like PTS, PT period, or PTS, or PT and space. So there is a root on the left, and you know that in given language model, word can be started from different 10 letters. Okay, so if you have something started from the root, then you have just 10 different options to start your new word, and P is one of that. So the freedom of transition from root to P is 10. And then, accordingly to your language model, if you have letter P followed by something, then in place of that something, there might be 4 different letters, like T and some others. And then the transition freedom from P to something else is 4. And further, if you have T after the P, then you can count transition freedom from T to something else, or from bigram PT to something else, or from bigram, which is starting from the root. And in all 3 cases, the transition freedom will be different. So we can count these transition freedoms in both directions, right to left and left to right. And we can count these transition freedoms in at least 3 different ways. You can count transition freedom from letter to letter. You can count it from n-gram to n-gram, and you can count it from n-gram to letter. And you can do it both in forward direction and backward direction. And making forward-looking statement, I will tell that this transition freedom metric appeared for us working much better than anything based on the mutual information and conditional probability. So the claims that I am going to make in this presentation are that first, the transition freedom appears to be superior over the mutual information or conditional probability measures for the purpose of unsupervised text segmentation. Further, if we consider different languages to be segmented and processed for lexicon discovery, then English and Russian require one specific way of handling this transition freedom measure, in particular the variance of the transition freedom, and Chinese requires a bit different specific way of handling it in order to maximize accuracy of the tokenization or lexicon discovery. And then you need to use what is called peak values described in the one of the reference papers, and I will elaborate what does peak value mean in a little bit later. Surprisingly, we have found that tokenization for quality for Russian and English may be as high as 0.96 to 1.0. So for Russian it was just 1.0, so that the quality was outstanding. For Chinese it was worse, depending on the quality assessment assumptions. It was in range from 0.71 to 0.92. Further, increase of the corpora didn't necessarily affect in better tokenization. So for instance, in English, using the Brown corpus, we have get the best, and the Brown corpus was the smallest across different corpora that we have used. So we having the tokenization model learned on the Brown corpus, we have get the best performance on the test set, and the test set was out of the training set. So the test set was taken from the other place. I will elaborate on the corpora and test and train set split in a minute. Further, the quality of the unsupervised tokenization based on transition freedom appeared to either same or even better than so-called lexicon discovery tokenization. So there is an approach in tokenization that instead of having rule-based tokenization pipelines, you create tokenization based on known lexicons. So it has turned out that for English and Chinese, the unsupervised tokenization based on the transition freedom worked better than even lexicon-based tokenization, because it's difficult to have all words present in lexicon for some unknown corpus. For Chinese, it worked worse. So for Chinese, we didn't manage to get unsupervised transition freedom-based tokenization working better than lexicon-based. And let me move ahead with our practical work. So for train corpora, we have used different sets of text files. For Chinese, we have used the two different corpora from Clue corpus. These are new Chinese corpus of overall volume about 9 gigabytes. For English, we have used 4 different corpora: Brown, Gutenberg Children, Gutenberg Adult, and Social Media. And results that we will be presenting are consistent across the English corpora. And in Russian, we have used Rusage, test, and previews corpora of different size, overall size about 1 gigabyte. And finally, and these train corpora were used to train the model, so to speak. Although it was not training, it was just the counting. So we were just counting the frequencies and evaluating the probabilities and transition freedom based on the adjustments of the letters and grams in the text that we have used for model building. And for test corpus, we have used completely independent data set from parallel Chinese, English, Russian in financial domains. So the Chinese English corpus was taken from public source, and Russian sentences were added by translation. And while doing the model building and actual tokenization, we have used different metrics indicators. So for the metrics that can be driving our tokenization, we tried metrics based on the probability and the transition freedom. And we were using derived metrics, like for probability, we have used deviation from mean, derivative, and Linas, can you please mute, because I think some echo is coming out of your speaker. So for both probability and transition freedom, we were using the raw metrics for conditional mutual alter probability in case of B grams, and conditional probability in terms of 3 grams and 4 grams and n grams. And then based on these probabilities and transition freedoms, we were using either deviations or derivatives. And also based on the derivatives, we were using so-called peak values suggested by one of the papers that we cite. And peak metric is one derived from the derivative. So on derivative, if you have some curve and you have derivative over this curve, and for example, if there is an increase in value and there is a decay in value, then the derivative is first gets positive and then it gets negative, right? So it goes, the derivative function crosses the zero line, and the peak takes the current positive derivative and subtracts the following negative derivative. So the peak function computes, actually subtracts the next value from the current value, and then it somehow amplifies the peaks. So that's and it has turned out that for Chinese, using this peak metrics has been useful to provide the superior performance. Further, the hyperparameters were combinations of the n-gram ranks that we were using for tokenization. So we were trying to use just separate individual symbols, bgrams, 3 grams, and so forth. And combinations of them, like unigrams and bgrams, unigrams and bgrams and 3 grams. Also, we were using trying to apply some thresholds for model compression. So, like we were after the counting the frequencies of all n grams, bgrams, and 3 grams, we were going through the counts and eliminating the symbols and links that are less frequent than a fraction of 1% from the top frequency number, or 0.1%. So we were trying with different thresholds. And also we were considering threshold for segmentation, like if we build the function over the sequence of letters using one of the matrix indicators above, then we decide that, okay, so here is the break of the segment in the text based on the respective metric exceeding the threshold. And finally, for evaluation of our tokenization, we were using F-measure for comparing the set of tokens found in the input text based on our unsupervised process, or and referring to the set of tokens found by rule-based tokenizer. The rule-based tokenizer was based either on a hard-coded set of delimiters in case of Russian on English, or we used open source JIBA tokenizer for Chinese. So here is how it works. For example, let's consider a tokenization based on the probability of single characters. It gets quite simple if we disregard punctuation. So you can see that, for example, if you consider the deviations of the probability of the symbols from the mean, so deviation from the mean above 0 shows that you just count probabilities of the letters, and you see that the space is always having superior probability, and you can safely break the sentence at the points where you have the space. Unfortunately, it doesn't work for commas, for periods, and for quotes and double quotes. So you can't use probability of a symbol to detach symbols from the text. Moving further, we can complicate it and use conditional probability. Mutual information, it appears similar to mutual information in case of bgrams. Like, for example, you are considering probability of M space versus probability of M. And then you see, and then you count the conditional probability of space appearing after M as probability of bgram M space related to the probability of unigram M. So you can count these probabilities in direction from left to right, and that is marked out with orange bars. So orange bars at every point correspond to conditional probability moving from the left to right. or you can count the conditional probability from right to left, and that is indicated with the blue bars. So blue bar corresponds that we are moving right to left. And so whenever you have the conditional probability value exceeding the threshold, either going from right to left or left to right, you can insert a segment, text segment break here. And what is between the segment breaks becomes a word that you can count as part of your lexicon or dictionary of punctuation marks. So as you see, you can't rely on it on conditional probability either, because there is no way to detach double quotes and commas from the words. So that's the reason why we are moving to transition freedoms, and we can get the raw transition freedoms on the first bar chart, and we can further derive the deviation from the mean at the bottom. And if you look into plots of the deviation from the mean, both right to left and left to right, at the bottom plot, you can see that you can clearly separate words, spaces, quotes, double quotes, commas, whatever punctuation you like. So that's and by the way, here's another example how you can handle the peak values. So at the top plot, you see the derivative of the condition freedom from right to left and left to right, and at the bottom you see what you get computing the so to speak peak value, outlining or amplifying the actual peaks. So as I said, for Chinese, this peak value was used to provide the greatest performance in terms of accuracy, and for English and Russian, the deviation was the best. By the way, here is an example of how you can do this segmentation of the Chinese text based on the transition freedoms versus conditional probabilities. You can see that on the top chart, the last 3 letters, glyphs, Chinese period, this letter and this letter, and this letter, they are all separated. But if you rely on conditional probabilities, the all 4 glyphs, including the Chinese period at the bottom, are not distinguishable. So you can't detach them one from others. They become single segment of the text, which is not true. Here's the example of how we did the hyperparameter search. So as I mentioned, if you select the single metric, and in the Chinese case, it was transition freedom peak. Even if you select the single metric, you still have the 3-dimensional space of hyperparameters. First of all, there is a filter that you use to compress the model, cutting away the low frequency transitions. Then you have the number of n's or n-grams, whether you are dealing with n-grams, b-grams, n-grams and b-grams, and so forth. So that's simple case. For Chinese, we have used only unigrams and b-grams because of the huge volume. So we weren't able to handle 3 grams on the computer with 32 gigabytes, but for English and Russian, we have used n-grams with n equals up to 7. And finally, there is a threshold for segmentation. So at which level we decide that, okay, we need to make the segment break here. So here's the heat map indicating that, okay, so with in the middle of here, there is a sweet spot where we can have accuracy at 0.71 with this set of hyperparameters. And for Russian and Chinese, the sweet spot, the F measure in this such heat spot was at level of 1.0. Here's now the most interesting part. So let me elaborate what we have here, because that's actually a sense of our results. So first of all, the first line corresponds the accuracy of tokenization based either on freedom-based tokenization, the unsupervised one which we're discussing, and the lexicon-based. And we can see that for English, tokenization is almost the same, 0.99. But further, we look into the accuracy of the lexicon discovery. So after we do tokenization, we actually go and check what is the accuracy of matching the words according to English lexicon. And we find that rule-based tokenizer makes it decent. So rule-based tokenization provides accuracy 1.0, and unfortunately, freedom-based tokenization gives you accuracy at 0.99. But then if you go, and by the way, we have also tried to do segmentation of the English text having the spaces removed. So we decided to make the problem really hard for us. So let's imagine we have no spaces, and here you immediately see that lexicon-based tokenization provides better performance than freedom-based tokenization, 0.79 versus 0.42. Further, we have tried it for Russian. So for Russian, the tokenization F-score was 1.0, and lexicon discovery also was 5.0. So for Russian, both tokenization and lexicon discovery was absolutely correct. So all words that we have identified were found in the English lexicon, and no false positive or false negative were found. However, and actually, lexicon discovery-based tokenization has appeared worse. It was just at level of 0.94 because of some unknown words present in the test corpus. And we also tried to remove spaces from the Russian text and see how it works. And we again found that lexicon-based tokenization in such case, of course, is better than freedom-based tokenization. And for Chinese, where we don't have spaces, right? So in Chinese, spaces are used, but they are used pretty occasionally. So in Chinese, spaces used like commas or semicolons or dashes in Russian. So in Chinese, spaces are used just to separate segment long sentences into phrases. And then in Chinese, we can see that indeed the tokenization quality of freedom-based tokenization is lower. It's 0.71. And lexicon-based tokenization is greater. It's 0.83. However, the lexicon discovery, even for Chinese, has appeared decently high, 0.99 versus 0.94, which can be obtained with rule-based tokenization. Also, we have managed to see that using this tokenization, transition space, freedom transition space, we can nicely cluster the letters into different categories. Like we can get all numbers in one cluster, we can get all punctuation marks in another cluster, and also we can separate now vowels and consonants into separate clusters. And we can do it either with cosine similarity or Jacquard similarity, and it has turned out that Jacquard similarity is a little bit more accurate. This is the work in progress, so we are still looking to do assessment of the quality of this clustering, like we discussed it with Linas, on the words on the side of the word clustering. Now answering the puzzle. In order to answer the puzzle that I posed in the very beginning, I need to tell a few things. So, of course, we can find a sweet spot of the hyperparameters which provide the decent and supervised segmentation, the lexicon discovery. So 0.71 for Chinese and 1.0 for Russian and 0.99 for English. But we can do that here because we know the ground truth. So we have the test corpus which we can compare with in order to find which set of the hyperparameters is the best. But the problem is that every language has its own set of hyperparameters. And even the metric used for segmentation for Chinese is one, and for Russian and English it is another. So we need somehow identify how we find which metrics and which hyperparameters are suitable for this particular language. So we were considering that we need some external measure that can assess the quality of segmentation without of knowledge of the language in advance, without of knowledge of the ground truth. And we have considered three basic metrics. Metric number one is Shannon entropy. So actually we use it, transform it Shannon entropy, we call it anti-entropy. So the Shannon entropy applied to the symbolic sequence is just about considering entropy of based on the probabilities of appearing the symbols in a sequence. And it can be extended for classical Shannon entropy deals with binary sequences, but it can be upscaled to dealing with any number of any domains of variables on the sequence. And we normalize our measure of entropy based on this number of states on the sequence. So it sits in range between 1 and 0, and then we subtract it from 1. So anti-entropy is 1 when the entropy is 0. And so we compare this entropy, the entropy of the text after the segmentation against the F measure of the text segmentation, given we have the ground truth or reference segmentation provided by rule-based segmenter. And we can see that for English, the connection between the Shannon entropy and the F score of segmentation is pretty good. So that suggests that for English, we don't need to know the ground truth tokenization in order to find the best hyperparameters. We can just refer to maximizing anti-entropy, and then we get this tokenization. Another metric that we were exploring was the coefficient of compression. So the coefficient of compression just handles tokenization as a way of compressing the sequence. So instead of having uncompressed text, a sequence of letters, you just bundle the letters into the words, and then you just store the sequence of words and have separate dictionary decoding the words into the sets of symbols. And then you can reduce the number of bytes you need to store the same amount of text. So that's coefficient of compression, and also see there is some dependency, good dependency between the coefficient of compression and that F score. Further, the metric number 3 that we have used is what we call cross-split F measure or cross-split F score, and it's defined as we take the whole input data set, we split the whole input data set into two pieces, like piece 1 and piece 2, and then on each piece we build the tokenization model, and we test then we tokenize each of the data sets with both models. So first data set is tokenized with the model trained on itself and with the model trained on the second set. And the second set is tokenized with the model trained on the first set and the model built on the second set. And then we compute the F score, average F score across these two different models. So we see to which extent the set of hyperparameters that we use assures that the models are consistent across the language. And here you can also see that this cross-split F score provides good connection between the consistency F score and the F score of the individual set. And finally, on the right, you see the combined metrics. So we actually combined these three metrics into one. And then the top, you see the top scores F score, top F scores corresponding to the top matrix, and also you see in the blue, so the blue corresponds to F score corresponding to superior metric, and orange corresponds to coefficient of correlation between the metric and F score. Now, so for English it looks pretty good, but for Russian it doesn't look that good. So for Russian it's a little bit more complicated. So you hardly can decide. Actually the entropy looks pretty good, but there are outliers which confuse the situation, and coefficient of compression may have much heavier clouds of outliers, and the combined matrix also is suffering the outliers in the right bottom corner. And for Chinese, it works a little bit worse, actually much more worse. So for Chinese, you hardly can rely on this universal matrix because there are outliers, and of course you can see that there is some dependency, like you can approximate this cloud with some line and say, okay, so indeed if you approximate this line, then the correlation is high. For example, here you can, for this kind of combined matrix, you see the correlation between the metric and the F score is close to 1.0, but unfortunately if you get, for example, this point corresponding to the highest entropy, you still get low F score at 0.3. And here is the answer to the puzzle that I have asked in the very beginning. So here you can see that the language 1 has turned to be Chinese, and language 2 has turned to be English, and language 3 has turned to be Russian. And by the way, the intuition that was suggested that appeared quite consistent across different people. I have run the voting on the Telegram, letting people to judge which language is which, and the answers were mostly correct, surprisingly. So I think I have dramatically run out of time, so I'm open to hear any questions. Now, let me see the chat. Okay, so I'm looking. Okay, so the goal of the random filter sequence is to randomly attempt transition freedom. So I'm just reading aloud what Linas has written. The goal of the random filter sequences is to randomly attempt transition freedom, or conditional probability, or MI, or Jacquard, or any one of thousands of metrics indicators, and let machine learning find the ones that work the best. Yes, I guess we are about the same thing. Thank you. Further comment from Linus. The goal here is to go back and forth. First, try freedom or conditional or whatever tokenization. You get something. It's ok, but it's low quality. Build a lexicon from this and got back and segment a second one using the lexicon. You must turn the crank twice, at least twice. Well, I would agree, yes. Further comment from Linus. Use any parameters, even low quality ones. Well, I disagree. Use this to build a lexicon. Segment a second time with the lexicon. It should be better. Collect statistics on the lexicon segmentation to build a second lexicon. This should be even better. Well, I agree. I'm still thinking that we shouldn't start with the low quality parameters. So I think we should somehow try to find some measures to get parameters at least not junk. So at least Linus, I think that these distributions are saying that we can get something which is above 0.5, and then starting from this above 0.5, we can run the process that you are suggesting to have things improved. So further, this Linus is saying this can be repeated 3, 4, 5 times. Each repeat should be better than the earlier one. That's would be something that I hope as well. And Russian has morphology. You also have to split terms from suffixes. Well, if you start going from letters, not from the words, I think you have some means to gradually learn suffixes and morphology after punctuation, and after you master learning suffixes, prefixes, and morphology after punctuation, you can move on to the layer of learning the grammar between words. Yes, I think that's true.
Anton, let me ask a question here. It's absolutely true that you need some kind of tokenization. Why do you need to stick to words? Let me detail on that. Linus has already mentioned Russian has morphology. And it might be natural to learn morphological units instead of words, because many morphological units have meanings per se. And meaning of a word, if we're looking at that, is some kind of combination of meanings of morphological units. Going further, besides Russian, English, and Chinese, there are languages like Turkish or German that allow you to combine almost infinite number of stems into a single word, like Hochdruck Dampfkraft Auflage. And of course, you might want to distill this kind of 5-stem word, but it's more natural. It looks to me that it's more natural to use these stem words as separate units. I would add that current tokenizers used in transformers, for example, most of them don't rely on words, but they rely on subword or sub-sentence units that are generated statistically.
Well, I don't have disagreement on this, so I think that might be quite true.
Thank you.
Okay, and Linus is confirming yes, stems should be treated as words, and also Linus is saying that the process is like distilling alcohol. You can't start with junk. You can start with junk. Well, each distillation, well, it's strong statement, yes. So actually with distilling alcohol, you can start with junk. You just need to have the right distillation process. Well, I can disagree with this. Interesting. Okay, so I think we are again running out of time, so we need to move further. And the next speaker is Victor Nasko with Zahar Panimash. Victor, are you ready to present your work? Okay, we see your screen. Go ahead. Thank you, Linus, and thank you, Nikolai, for your comments for discussion. Victor, please go ahead, and Zahar, please.
Yeah, good evening. My presentation is about fast experts tuning, better domain adaptation method for transformers efficient tuning. What is the main idea? We have a challenge. You know, generative models require a huge GPU power to train off of weights. we suppose a solution train not entire neural network, but only some layers. Here is the outline of report. We will talk about adapters. What is adapter? What is the common types of adapters? A mixture of experts from Google. We also present a fast experts tuning technology. The idea is similar to Google's mixture of experts, and here we will present our technology for the first time for English-speaking audience. Next, GPT fast tuning library, code, and GitHub. And also we will outline some examples of interpretable generation with BART, transformer BART, not BERT, and interpretable generation with RuGPT3, which is clone of the famous GPT-3 from OpenAI. And now Zahar Parimash, as the main developer of fast expert tuning, please continue.
The basic idea of effective tuning is to efficiently train large models on a relatively small data set. There are different methods to quickly tune large pre-trained language neural network models. Among these methods, we can classify prompt tuning. There are a few short and adapters. Let us consider adapters in more detail. They are parameter efficient. They adapt only a very small subset, often less than 1% of model parameters. They are often modular, i.e., the updated parameters can be retrieved and shared independently of the base model parameters. They take up significantly less disk space and the intermodal. Next. Adapters have a common feature, which is to add one or more adapter layers and then train only them. Some adapters are trained for one task. For example, the bottleneck scheme, in which the adapter is two layers. The first lowers the dimensionality of data, and the second increase it. This schema is very similar to classic autoencoders. Other adapters can be trained for many tasks. Inside them, there is usually a classifier that determines which task currently running. The classifier can both switch adapters and mix their outputs in different proportions. This, for example, is done in mixture of experts, adapter fusion, and fast expert tuning, which will be diffusion later. In some cases, an adapter is part in parallel to a layer, and the outputs are added together. LoRa is such an example. The classic Moore architecture introduced in 1990s, consisted of several expert neural networks then performed the classification task, and a neural network that gave weights to the classifier depending on the input data. After activation, the experts were summarized with these weights. This architecture allowed individual networks to be towns to individual tasks, and then use it all together, which is very similar to weighting bagging. In 2022, there was an article of the Google blog about using Moya as an adapter in the encoder block in transformer in computer vision and natural language processing task. The link to this post is on the slide.
I'll continue. Here, let's describe what's going on when you train with the help of fast sparse tuning technology. Take a look on the picture. Here's a yellow arrow to the time of training. Here is a small numbers. You can see here that entire training takes about a minute and 22 seconds for 3 epochs. Here is below the image. You can see a training log, and you can see also that loss it's also continuously decreasing. So we have a task. We need to generate an article or a replica, for example, for chatbot setting. So you don't need to train entire network. You know that GPT medium or large takes a lot of time, about an hour or 2 hours, depending on the nature of the model, its number of weights. It takes a lot of time. It takes a lot of money. So we have now the following numbers. We have a 50 times faster training for RuGPT-3 medium model. RuGPT-3 medium is 760 million parameters. It's a medium model, a clone of the famous GPT-3 from OpenAI. How it works? We don't train all the weights. We only train our layer. So training becomes really faster. And text. Let's describe what's going on here on the image. Above image, we have only 9 training texts for this task. This text written in Russian, I will explain. In English, we have a gaming setting. For example, we can give a text about a stalker video game and some text about other video games. And you can see here only 9 training examples. So we have now some kind of few-shot setting. And take a look on the bottom image. We can create a generator, text generator from a new model, and then after training, after a model was trained, can get a stylized output for the gaming setting. For example, what's going on here? We have only 9 samples, but we have a tuned Wkshp model, and what we have achieved here. You can ask why you show a Stalker video game example. Let's explain. That's because a Stalker is a literature, a video game, and it has a lot of other explanations and mentions in the internet. So here we can show that our model successfully understand that our setting is devoted to the Stalker video game, not a literature character. So we achieved a controllable generation. So we can do this with a lot of other settings. And our system, there is, you can see a parameter set variety of answers. There is a contribution to the probabilistic model to the generation. At value 0, the temperature of the probabilistic model tends to 0, and when we have value 1 to infinity, which leads to the fact that the generation is approximately the same as before training. Of course, the adapter layer will cause the change, but it is significant. You can see here on the slide that generation starts from the word seria, is a series of video games, and it successfully continue with the game theme or game topic. It consists of a classifier of experts and adapters consisting of a single linear layer and a probabilistic model. Initially, the layer is initialized as a unit matrix. The output is a probabilistic model, which is trained separately from the basic model, and it gives the probability of the next token. Later on, the probabilities from the complementary model and the main model are multiplied, and the whole system learns a single adapter layer using backward error propagation. This approach allows to train the neural networks much faster, providing the additional probabilistic model is quite simple. A different probabilistic model and adapter layer are trained for each task and then mixed in proportion to the activations of the classifier, which is very similar to the mixture of experts approach for training GPT and other transformers. But unlike the mixture of experts, we use a small trained model in parallel with the main neural network, in our case, GPT. The choice of model type greatly depends on the dataset size. So for different tasks within the same fast experts tuning algorithm, a different model types can be chosen. Unlike a mixture of experts in the mixing block, there is only a weighted summarization of vectors, but also multiplication of probabilities from different probability models experts. Besides, not all outputs are summed up, but only the top n outputs, which allows not to start all experts every time. Here on the slide, you can see a little, a brief comparison of FET to other methods you can use. For example, here on the left there's 2 images that show generation control. For example, you can fine-tune a GPT model to achieve a overfitted setting, then you will achieve a control for generation. For example, if you have a chatbot setting, you will be sure that a model will generate answer to the common question, what is your name? It will be a stable answer. So if you have overfitted setting for GPT-3, you can get stable answer, but it takes a lot of time and money. So fast expert tuning, what I would like to emphasize on this slide, fast expert tuning is not devoted to the downstream, is not devoted to the broad tasks. Fine tuning is devoted and used to get a broad task. You can fine tune, and then you can use a fine tuned model to get a solution for chatbot setting, for news generation setting, and so on. But fast expert tuning is devoted to the narrow task. We call often as a downstream task. So don't use fast expert tuning for broad tasks. GPT fast tuning is our library for fast tuning for GPT. In essence, fast tuning is an adapter consisting of a single layer, a linear layer, and a probabilistic model. Unlike that, this approach does not use many experts, but only one adapter and one very simple probabilistic model. The probabilistic model here is a mask of tokens and the data set of their normalized distribution. After training, we write the result of matrix multiplication of the adapter layer and the classifier layer into the token classifier layer. And we write the algorithm of the distribution into the bias weights, which allows us to use previously written methods based on the Hugging Face tools without any modifications in the future. Here you can see screenshots of our GitHub. It's currently private, but we have this library, and by request we can send a YouTube demonstration. This library is fully working. Demonstration is super fast because you can see about 1 or 2 minutes for training an entire model for 760 million parameters, and you can request, and we will show a live demonstration or send a YouTube demonstration. Here is a slide that shows that we can use BART-based controlled generation. In many practical problems, BART performs significantly better than GPT-like models. Therefore, we plan to develop fast expert tuning for BART in the future. What I would like to emphasize on this slide, here on the image on the left, you can see some keywords or entities you can put on the right places on the generated text. You know that GPT has a bad abilities to control text, yeah, but BART has these abilities, and you can use some keywords, some entities, and you will generate text that BART will put on the right places in the right morphological forms. It's a very cool achievement comparing a BART setting to the GPT setting. And here is GPT setting, also controllable, interpretable, and controllable generation, but it's some kind of worse. You can achieve a text using also you can use keywords, you can use a prompt generation, but it behaves in some features worse than BART setting. That's a final slide. You can ask questions. Zahar will answer because he's a developer of this technology. And thank you.
Thank you, Victor. Thank you, Zahar. Any questions to speakers? So I have a question. So Victor, does it mean that your technology is so that you need to train the model first on the corpora of the dialogues and after or text, and after then you just apply your experts to fine-tune the model?
You can use both. You can use both settings. You can use a broad corpora that consists a lot of text, thousands or million of text. But after this, a simple fine tuning, you can use fast expert tuning. But also you can apply fast expert tuning to the model from the box. I don't know how to say from the box. Yeah, model, not touched, not trained on the any corpora, and you can achieve a few shot settings. You can get a little number of samples, and you got a topical generation. Maybe Zahar will add.
Okay, and by the way, when you train the model, do you train the model based on the tokenized text, or do you use word pieces, Bert's word pieces, or what? So what is your tokenization model for the language learning?
To Zahar.
We using Hugging Face tokenization.
Which tokenization?
Hugging Face tokenizer.
Okay. Okay, so it tokenizes words, so it doesn't work with word pieces, right? Like Google's BERT.
GPT-2 tokenizer we use.
Okay, can you type it in to the Zoom for Linus? So GPT-2 tokenizer or Hummingbot or Hugging Faces tokenizer? Still not clear.
Class in Hugging Face. Class naming GPT-2 fast tokenizer.
Okay, can you send the link to the Zoom?
Okay.
Yeah, just curious. Linus is asking, so please send the link to the tokenization to the Zoom. Okay, so thank you, Victor. Thank you, Zahar. If no any other questions, let me check the YouTube, by the way. If we have, okay, no questions on YouTube still. So let's move to our next speaker, and next speaker, Mukul Vishwas, will tell on how we can use interpretable sentiment analysis and cognitive distortions analysis models connect from social media in connection with market dynamics. Mukul, can you share your slides?
I cannot share it right now because
okay, Victor, can you stop sharing?
How to stop?
Or Zahar, who is sharing the screen. Okay, Mukul, can you try to share now? Okay,
I
we see
hope
your
you all
screen.
are able to see. Okay, so
Yeah, go ahead.
hello everyone. Hello everyone. So the topic of my presentation is sentiment and cognitive distortion, mining in social media. So in this presentation, I'm trying to demonstrate how we can analyze the potential connection between the different sentiment metrics and the cognitive distortion. And for our experiment, we collected around 77 feeds on Twitter and Reddit, and we computed 19 sentiment metrics and total 19 metrics, in which 4 are sentiment metrics and 15 are cognitive behavior distortions. And this cognitive behavior distortion is the extended work of historical language records, revealing a surge of cognitive distortion in recent decades. So they calculated 15 types of cognitive distortion in their work, and we use those distortion in our work as well. The main part and the very important part is we need a huge number of data to calculate this type of distortions, because they are based on n-grams. After that, we also tried to see, we also experimented with more than 20 plus models, and we choose agents because first of all, it outperformed other models and because of its interpretable nature. So I'm going to talk about more about the model and all these metrics in further slides. So first of all, I want to give a brief description about the cognitive distortion. So as I described earlier, that we are using 15 cognitive behavior distortions. Those are mind reading and catastrophizing, labeling. These are some of that. But how we find out this distortion? This distortion can be found in the tweet or in any news, and it can be found how the writer writes his feed. So if he is using backgrounds like will fail or will go wrong, it can be it will be a distortion which is known as catastrophizing. And if he's using some backgrounds like everyone knows or everyone thinks, it will be considered as mind reading. So we have 15 metrics, and we use these n-grams to calculate all these metrics. And we are using agents model to calculate the sentiment metrics, and this is interpretable model, and this is interpretable because if we give a sentence or a feed to this model and it return back a score, it may be positive, negative, a combined sentiment or contradictory score. So we can ask this agent that why you are giving this score to this feed. So it will give us that based on these words or based on this n-grams, I provided this score. And it's very easy to adjust as well. So we can modify this agent model as per our requirements. So it's interpretable and easy, and we can modify its performance as well. And this is n-gram based, and we are using 8,200 negative words and 3,800 positive words. And we have more number of negative words because most of the positive words can be converted to negative word just by using negations. So So if we have good, we can easily convert it to a negative word or a negative diagram by just using not in front of it. So not good. So most of the positive word can be converted into negative. So that's why we have more number of negatives. And the advantage of using agents model is its property of priority on order. So what is priority on order? So as we know, it's n-gram based algorithm. So, and it converts the total views to n-grams, and it gives priority to higher n-grams. For the example, if we have a tetragram, like not a bad thing. So it's this tetragram is completely a positive. It will give a positive sentiment. But if we consider lower n-grams, which is bad thing, not and bad, this will give negative sentiment. So because of its priority or order, it will give a more reliable sentiment score. And because we are using this priority on order, it resolves our negation problem. As I described earlier, most of the positive word can be converted to negative just using the negation. So using priority on order, we can resolve this issue. And moving on about the sentiment metrics. So we are calculating 4 sentiment metrics, positive, negative, which are self-explainable, and total sentiment, which is just the addition of positive and negative. But most important is contradictive. Suppose in a feed we have first half positive and second half negative, or vice versa. For the example, honestly, I don't like crypto stuff, but I am happy that it makes me richer. So first half is rather negative and second half is positive. If we look into the positive aspect, it has positive score and it has negative score both. If we take total sentiment, it will become 0. So this sentence has some meaning and some score to it, but if we are calculating total sentiment, it's become 0. It's become kind of useless. But if we calculate the contradictiveness, so it will give us 1. So this will make a huge impact for the prediction purpose. So that's why contradictive is very important, and that's why we are calculating it. Moving on, I want to show how we try to establish the causal connection between social metrics and sentiment metrics and the price movement. So on the first chart, in the blue line, we can see, or we can consider this as a positive sentiment or pumping indicators on, and the orange line can be considered as a negative sentiment or dumping metrics or dumping indicators. Okay, and on the second chart, it's the price movement of any asset, suppose Bitcoin or any other market. Okay, now in this third chart, this plot is the derived matrix of price difference. So if we have a spike of price at 0.2 to 0.3, then we can see that this price difference goes from 0 to 1 at day third, because there is the price moving upward. So this price is going up. Now, in causal connection, we try to figure out whether this movement of price caused by this positive in or this pump indicator or not. So how we do that? We do the shift of this price movement to a -1 day, or just move this price difference to 1 day back, or slide this to 1 day back, and take the take the correlation between this pump indicator and this price. So if we move it back, we can see this peak matches this pump indicator, and that's why the correlation here is 0.77. And same goes for the negative indicator as well. If we shift this price difference to 1 day back, we can see this price which is going down is matching with this dump indicator or a negative sentiment. That's why we have negative correlation here. So we can see here by shifting the price or price difference, we can see causal connection between the pumping indicator or the pump signal and the change in price. So it can be done in negative direction and it can be done in positive direction as well. Like by doing this analysis, we can see which come first, the price making some impact on the market or on the sentiment, or sentiment making some impact on the price. So this type of analysis can be done by this causal connection. Okay, so about the model selection, as I said earlier, we tried more than 20 plus models on a test corpus, and these are the peers correlation of between the sentiments, and we can see that agents model outperformed all other models comparatively, and this is very easy because of its interpretable nature. It's very easy to improve its performance as well. So Agent Plus is the modified version of agents. We used crypto domain specific corpus to improve its performance, and the correlation is improved significantly from 0.35 to around 0.58. It's a huge jump. So we use this for our prediction purpose. And here we can see the causal connection between 4 sentiment metrics and the price difference. And we shift this from 7-day past to 7-day before. And here we can see at -1, there is not much correlation between the price difference and individual sentiment score. Here we can see that there are some causal connection on day 1. It means the price difference is coming after something is posted on the social media. This is true for the total sentiment, negative sentiment, and here we can see there are some correlation between the price difference and positive sentiment 1 day before, and there is some correlation between contradictiveness and the price difference 1 day before, but it's not significant enough so that we can make some prediction based on this. So to overcome this problem, what we did is we combined all these 4 score and introduced channel weights, and this channel weight is calculated by how frequent the posts are available on these channels. So we introduced that weight, and we combined all these metrics, all 4 metrics and other metrics as well. And here we can see improvement in the correlation. Now we can have a significantly higher correlation 1 day before the price changes. So it can be considered we can consider this as an indication that something happened 1 day before price change. And now we just have to find out what happened. What are the parameters which cause this price change? So to find out that, I want to show you a picture, which is the elaboration of this. So this is the combination of all those metrics. and this is the individual matrix or the derived matrix. So here we can see that in blue line is the price difference, and this orange line is the cognitive behavior distortions. So here we can see that cognitive behavior distortions comes first, and then there is change in the price. And here we can see again there are some changes in the cognitive behavior, and then there is change in the price difference. But this is not always the case. There are some cases when first comes the price change and there are some changes in the cognitive behavior. But uh, but we can see that trade count is more predictable than the price difference. So this is more reliable because there are the presence of cognitive behavior changes come more frequent before the price change. So here is the change in or the spikes in the cognitive behavior, and then comes the price change. We can see the same thing here, change in the cognitive behavior, and then there's change in the price. Same can be seen here as well. So trade counts are more affected by this cognitive behavior or the metrics as compared to price difference. Now we see that there are some changes one day before, but which metrics are more reliable or which are more correlated with the price difference. So here these are the individual correlation of each of these metrics, sentiment, and the cognitive metrics with the price difference. So here we can see fortune telling have correlation greater than other, but not high enough, which can be as we can see here that price difference are predictable, but not that. So that can be verified here. The correlation is there, but it's not high enough, and not I can see not that much reliable as well. But when we look into the trade volume or the trade count, the correlation one day before is much higher, and it can be this metrics can be considered for the trade volume prediction as well, or we can make some synthetic synthetic metrics from these metrics as well for the prediction. But we do have some challenges, and we are working on some other tasks as well to improve the predictability. First of all, in our model, we do not have weights for different words. Like if someone is using good and someone and the same person is using excellent, so excellent should have more weight than good. So in our in the model, there are same weight for each and every model. So we should have different weight for different words, so we can have a more reliable sentiment score. The another challenge is context aware n-gram. So for the example, the weather is cold, but VTC is shining. So in this example, we can understand that this is about the Bitcoins, but it is not clear for the model whether we are or the writer is talking about weather or about the crypto market. So the model needs to be context aware. The another challenge we have is current news agenda aware n-grams. So we saw while we are doing manual tagging that there are a lot of news or a lot of tweets which are related to current situation of crypto market, but it's very hard to distinguish between it's very hard to distinguish whether these are related to crypto market or this is related to something else. So the model needs to be understand about the current situation of the markets as well. And the another challenge right now is sarcasm. for the example, anyone, for the example, I like how these friendly senators have agreed on the law increasing the government control over crypto. So it seems positive neutral, but it's more negative. So it can confuse the model, and it can just assume or create n-grams, and it can make it positive or negative. It can classify as positive or negative based on the positive or negative dictionary it has. So model needs to understand sarcasm as well. Apart from that, we have idioms, and our model does not support right now non-text data. So we are working on this, and we will try to improve our model for all these challenges. And thank you. That's all from my side. I am open for any question you have.
Thank you, Mukul. We have a couple of questions from the YouTube. So first question is that from Miss H. So it can discern good or bad, but not the state or context of the text. For example, can it discern drunk text versus sober text?
No, it's completely depend on the n-grams. If he is drunk and he is writing movie is good, and he is sober and writing movie is good, it will not distinguish between the states of the writer. It just completely depends on the word he is using.
Okay. Thanks. And another, yes, I would support that. So actually, drunk text versus sober text would need some understanding of the context, and actually not even the context. It would understand the mental state and the reasoning style of the writer. So I think it would be difficult to handle in approach that we are presenting here. And another question also from, I believe, the same person about, no, the question is from Tommy Vijama, whether the cognitive distortions and cognitive biases are the same. Okay, so the answer is no. So there are different things called cognitive distortions and cognitive biases. So what we analyze in this work, sorry Mukul for answering for you, because actually I have to answer this question. So what we analyze here, yes, thank you. We analyze cognitive distortions. So cognitive distortions are coming out from cognitive behavioral therapy, and they are focused on detecting the psychological state which are associated with different forms of cognitive disorders like anxiety or depression. Okay, and the reason we have chosen these cognitive distortions is that there is a paper published and referenced in our work on Archive. And in this paper, the researchers have studied the whole almost 100 years of the world literature in English, I believe. And they analyzed these almost 100 years of English literature for such patterns. And they were finding significant correlation between the expression and of these cognitive distortions associated with periods of wars, economical depressions, and other negative effects in social and economical lives. And this paper was associated with the actual linguistic patterns corresponding to these cognitive distortions. So we just have reused these patterns, and these patterns actually are known to cognitive behavioral therapists who use these patterns in their everyday practice. So we just have used these patterns and applied these patterns to our data. And that's about cognitive distortions. And cognitive biases is something more complex. And cognitive biases are more about style of thinking, which might not necessarily be associated with certain disorders. For example, I may be thinking more generally or more specifically. I may be more biased towards my own knowledge, or I might be more trusting to someone else's knowledge. Of course, there is certain overlap between the cognitive biases and cognitive distortions. For example, there is such a cognitive distortion called personalizing. Like, if there is anything bad is happening, then I am attributing this badness to myself. So that means I am suffering the personalizing. On the other hand, if you consider cognitive biases, there is a cognitive bias called self-assessment, which is also form of or egocentric bias. So egocentric bias is a kind of cognitive bias when I am centric about my own person, but that might not be negative. So there is some overlap, but it's not quite overlapping, and the purpose, so there are two different classification systems which are somewhat overlapping, but generally they are different and they serve different purposes. And of course, because for cognitive biases, you need to actually have high-level analysis of the argument structure. I believe you cannot figure out the cognitive biases using such simple technology as n-grams, even with that priority or another feature that Mukul has described. You need actually common sense reasoning and relationship extraction, and even argument discourse and argument structure analysis based on the semantic relationship extraction out of the natural language text. Yes, Mukul, any other comments?
Yeah, I just want to add, like, if we have, for this type of study, we need a lot of data, first of all. And another thing is, when we are talking specifically about crypto market, and when crypto market is going down or going up, we can see this type of distortion in the news feeds which we are collecting. So people will actually show this kind of distortions. So the people which have more influence on the market, they started to say, when market is going down, they started to say that market will go up, or everyone knows that after its dip, it will go up. So this will impact the market. This type of distortion will impact the market. So
okay, thank you. And there is another answer from Linas, how the Yajin sentiment models created. Okay, so I'm just sending the link to the describing the Yajin sentiment model, and it was created first taking different dictionaries of words and n-grams known for positive and negative sentiment from different sources. Then there was some manual process of merging these dictionaries in a unified dictionary. And after that, there was long process of testing this dictionary against real-time news being collected by AI-Gen's news aggregation system, and refining this flow of sentiment analysis assessments and adjusting all errors and misperceptions and misdiscernments of the positive and negative sentiment manually made it possible to have the current dictionary of n-grams for positive and negative sentiment. Moreover, for the purpose of the project that Mukul has presented, we have also did tailoring of that dictionary against crypto market. So what we have done, we have created some test set, and we evaluated this test set based on our original model, and we found some number of misclassifications. We were looking into the reasons of these misclassifications and understanding specific patterns that are attributed to financial domain, and we were adjusting and extending the positive and negative dictionaries accordingly. So yeah, so actually I think that we can also, the other thing that you can do, you can actually improve the process of building such dictionaries by means of using unsupervised or supervised learning. So training your models based on the some marked up positive and negative sentiment corpora. You might extract the patterns from the models, and then you can further store these patterns in the interpretable form and edit these patterns accordingly to prevent some things that are learned in a wrong way, but that's kind of work in progress. Okay, any other questions? No any questions, so I think we are, let me check by the way the YouTube channel if there are any questions. No, just appreciation of our talks. And do we need to have some further discussion? Does any of speakers have some questions or ideas to bring to discussion? Linus, Nikolai, Victor, Zahar, Mukul.
Actually, I was pretty
Okay.
excited when I was.
Yeah, go ahead.
Actually, yeah, I'm saying that I was pretty excited when I was listening about the context. So how we can extract the context of the news, and we can create a tree, and we can get the context of the total sentence which we are processing. But it's come out that still this work is still in progress. Otherwise, we can use this to integrate with our work, and we can solve the problem which we are having right now about the context aware news.
Yeah, actually, also I am very happy that Linus was able to make this event under the stressing conditions that we and Linus are aware. So thank you, Linus, and thank you, Nikolai, for joining this. And I think we have something to work on together with you and Linus in unsupervised language learning in all aspects. Starting with letters and morphology, further to grammar, and sorting out how do we account the context, and sorting out how we marry the transitional freedom with the conditional probabilities. So let's stay in touch. And Linus is saying, I have ideas, but they are hard to articulate in such a short, small space. Yeah, so let's work out. And by the way, Linus, just so you know, Nikolai and myself and Mukul and Victor, we are all massively using Telegram instead of Discord. So if you manage to get on Telegram, there is a whole interpretable natural language processing channel on Telegram where we discuss the matters of the last year workshop, and Rob Freeman there as well. So if you manage to join the Telegram, then we will be happy to have discussions there with you. Otherwise, we have email, and we have your Lean Grammar email list, and we have your GitHub issues where we have all these discussions. Okay, and Linus, by the way, you mentioned that there are other people on Discord, and I'm not sure what particular Discord channel you mean. So if you can share the Discord channel in email, So maybe we can benefit OpenCog Discord. Okay, okay, okay. So any other questions or comments or suggestions? Okay, so if not any else, then thank you everyone, and thank you SingularityNET organizers who have made this event this year, and hope we have the same event with more results in a year from now. Thank you everyone.
Thank you. Bye-bye.
Thank you, Peter. Bye. Thank you, Linus, Alay, Victor, Zahar, and Mukul.